For this mini lecture on Module 8, One-way ANOVA, we're going to work through an entire ANOVA example together. This example is the one from your book, and looking at if the type of drug taken influences the number of psychotic episodes. Our first step, of course, is to construct a statistical hypothesis, and our null hypothesis is that the population mean number of psychotic episodes will not differ between any of the drugs, and our alternative hypothesis is that at least two of the means will differ. It's our standard ANOVA hypotheses. So the independent variable here is the type of drug administered, and the dependent variable is what we're measuring, which is the number of psychotic episodes. We need to establish our statistical decision rule, and for the entire study we want our alpha to be 0.05, and then we're going to calculate the test statistic for a third step. First thing we need to do is collect data. So we have our three different drugs here, A, B, and C, and then the numbers underneath that represent the number of psychotic episodes. Given this information, we can calculate the mean for each of the treatments and the standard deviation. So the numbers you see below, so n is just the number of samples in each of the treatments. X bar is the mean for the treatment, and then our standard deviation is calculated below. Because we're doing an ANOVA and we're going to be partitioning sum of squares, we also need information on the grand mean. So this column over here with grand has the total number of samples, which is 12, right? Because there's our three different drugs and there's each 4 samples for them. The overall mean, and then the overall standard deviation from the samples. We could plot our data just to get some insight into the relationships that we might be expecting to see. So now here we have a bar graph because we have nominal data with our 3 different types of drugs, and then we have the number of episodes that are shown. And for each of these we have a standard deviation plotted for it. One of the assumptions of ANOVA, remember, is that we have equal variance, and variance is the standard deviation squared. So here by looking at our standard deviations we can tell that they look quite similar. And I always think that plotting your data as a first step is a good thing, because whenever you do statistical analysis you should never be surprised by your results. So here it might look like A and B are quite similar, but drug C has much lower number of psychotic episodes. But does that hold up with the statistics? We have to do that to figure it out. So let's work through this example. So here's the data with the number of drugs that I already showed you. And the symbols here are a little bit different, because what I'm going to do with this example for calculating the sum of squares is that I'm going to be doing it slightly differently than the book does. The answers at the end will be exactly the same, but intuitively this method that I'm going to show you might make a little bit more sense. But you need to know some terminology first. So here we have our 3 different drugs. This is the exact same data you saw before. Now we have N sub I, where I is representing the treatment. So I represents the treatment. And then when we see something like this, I and then a plus, that means all samples within that treatment. So the plus means all samples in the treatment over here. Right? And when we calculate the mean for a treatment or the standard deviation, we're doing it for one treatment. This is for one treatment, and we're using data from all of the individuals in that treatment. When we look at the grand mean is this. That's the grand mean. And the grand mean is calculated based on all treatments and all individuals within those treatments. So that's why it's based on a plus plus. So when we think of it this way, we have our treatment is I, and then the plus means all individuals in that treatment. This is all treatments and all individuals within those treatments. So we have our grand mean here, which is 5.42, and we want to know when we're doing an ANOVA how much of that variation that we see in the data is due to treatment effects. So how much do the treatments vary from the grand mean? And then we want to know about the error, which is how much do individuals differ from their treatment mean. So this is the alternative way to do sum of squares calculations based on partitioning the variation. And this equation might look a little bit intimidating, but it's really not if we think about it. So this is our sum of squares total. So this is how much does an individual data point, so from treatment I, individual J, so we have an individual sample, and how much does that differ from the grand mean? That's all it's saying. And it's a sum of squares, so we sum the squares. And we're going to be sampling over all treatments and over all individuals. And like I said, it's not as scary as it looks. So when we're looking at the data, you'll notice that this 5.42 is our grand mean. And then this first row of data represents these individuals here. So 9, 8, 7, 5. You see we have 9 minus the grand mean, 8 minus the grand mean, 7 minus the grand mean, and 5 minus the grand mean. So this data represents these individuals. Of course, those differences are all squared. So this row here represents the individuals from drug A. We have to do this across all treatments and all individuals. So the second row represents drug B and each individual. So you could go and look at that other table to see that there's a 9, 7, 6, and a 5. And then the third row represents drug C. So this is the sum of squares total, the total variation. Now this 22.194 is based on drug A, the 15.861 is from drug B, and 46.861 is for drug C. And then we just add those together and we get our sum of squares total. So that's sum of squares total. Sum of squares total is based on treatment effects and on error. So our treatment, this is how much does the treatment mean vary from the grand mean. So here again we have the grand mean. We have our treatment mean. And all samples within a treatment have the same treatment mean. So this is the number of samples in a treatment. Right? Because all samples within a treatment will have the same treatment mean. And we're summing across all treatments. That's what this summation means. So now we have 4, which is the number of individuals in the treatment. 7.25 is the treatment mean for drug A. And 5.42 is, of course, the grand mean. Right? 7.25 is the mean for drug A. 6.75 is the mean for drug B. Again, we have 4 individuals. And 2.25 is the mean for drug C. And again, we have 4 individuals. So 6.75 is the mean for drug B minus the grand mean. Again, there's 4 individuals in that treatment. And then we have drug C. So this is the sum of squares that we're calculating for the treatment effect. We sum those up and get 60.667, and that's our sum of squares due to a treatment effect. So the total sum of squares is partitioned into variation due to the different treatments that are assigned, and then due to error. So error is the last calculation that we have here. So error now is representing an individual sample and how much that individual sample varies from the treatment mean that that sample belongs to. Again, summed over all treatments and all individuals. So now we have the individual data points for drug A. We're still doing drug A in the top row here. And now the second value is the drug A mean. So that's the treatment mean. Okay, so it's the individual scores minus the drug A treatment mean in the first row. Of course, those are all squared. The second row is representing drug B. So now they're subtracting 6.75 because that's the mean for drug B. And then the third row here represents drug C. These are the summations for each row. And then our sum of squares error is equal to 24.250. Recall that sum of squares total is equal to sum of squares due to the treatment effect plus the sum of squares error. And 24.250 plus 60.667 equals 84.917. So that's an alternative way to calculate the sum of squares that makes you think about how to partition it, and it's a little bit different from the book. I prefer to think about it this way. So now that we have our sum of squares, in order to calculate our ANOVA, we also need our degrees of freedom in order to be able to calculate our analysis of variance. The degrees of freedom total is the number of total scores in our samples minus 1. Here we have 12 minus 1, which is equal to 11. Our degrees of freedom for a treatment is based on the number of treatments that we have minus 1. We have 3 treatments because we have 3 different drugs minus 1, so our degrees of freedom for the treatment is equal to 2. And then we also need our degrees of freedom error, which is the total number of scores that we have minus the number of treatments. So that's going to be 12 minus 3, which is going to equal 9. And when we look up our critical value, it's going to be based on our treatment and our error. So it's 2 and 9 is what we'll end up looking up for our degrees of freedom. When we do an analysis of variance, mean squares are very important because mean squares are variance. That's where the variance comes from. And we want to know the variance due to the treatments versus the variance just due to random sampling error. So our mean square for our treatment, and we're going to go over this in ANOVA table in a minute also, is the sum of squares treatment divided by the degrees of freedom treatment. So it's 60.667 divided by 2, which is equal to 30.333. Our mean square error is the sum of squares error divided by the degrees of freedom error, and these will always match. If it's error in the numerator, it's error in the denominator. So it's 24.250 divided by 9, which is 2.694. And then we can calculate F, which is our mean squared treatment divided by our mean square error. So it's this value, 30.333, divided by 2.694, which is equal to 11.259. So we just did a number of different calculations. We calculated our sum of squares, our degrees of freedom, our mean square as well, and our F calculation, but there's a much better way to sort of organize all of our thoughts about this, and that is to create a summary ANOVA table. In this, we write out our sum of squares. So our sum of squares for a treatment, which is drugs, is 60.667, and our sum of squares error is 24.250. Our total sum of squares is 84.917. We calculated this, but you also know as a check that if you add these two together, they should equal the total. Our degrees of freedom for a treatment is equal to 2. Our degrees of freedom error is 9. And our total degrees of freedom is 11. Again, these ones sum up. When we calculate our mean square, so the mean square treatment effect is 60.667 divided by 2, which is equal to 30.333. So it's just this value divided by that value. Our mean square error is going to be this value divided by that value. So it's 24.250, or sum of squares error divided by our degrees of freedom error, which is 2.694. These don't sum up to anything. This is nothing that makes any sense. So the total mean square we don't calculate because it's meaningless. And then our F is our mean square treatment divided by our mean square error. So if there's more variation, remember, due to treatments than there is variation due to just a random sampling error, then we would expect to actually see a significant difference between the means. So when we divide these two values together, we get 11.259. Okay, so that's our F statistic that we've calculated. And then we need to do step 4, which is to compare our test statistic, so our F calculated, to our F critical, and draw conclusions. So in order to calculate our critical value for F, we need our degrees of freedom for our treatment and our degrees of freedom error. So our degrees of freedom for our numerator, which is treatment, is 2, and our degrees of freedom for the denominator is 9. The ones in light color here are alpha for 0.05, so our critical value is 4.26. So our F critical is 4.26, and our calculated F is 11.259. So if we draw our distribution of F, remember it's skewed distribution, our F critical is equal to 4.26. and our F calculated is equal to 11.259. So our F calculated is greater than our F critical. Therefore, we reject our null hypothesis, and we would conclude that the mean number of psychotic episodes experienced differed significantly between at least 2 of the drugs tested. So our conclusion again is the mean number of psychotic episodes experienced differed significantly between at least 2 of the drugs tested, with a p-value less than 0.05. At this point, all we know is that 2 of the means differ. We don't know which of those means differ. In order to figure that out, we need to continue on and do a Tukey's test.